Hey geometries. So next we're going to take a look at mid-segments and bisectors in triangles. We're going to talk about a bunch of cool triangle segments in the next couple weeks before and after break. So we're going to start here with mid-segments, and then we're going to cover a little bit of the segment and angle bisectors, and then we'll get to medians and altitudes in a little bit. All right, first some definitions. A mid-segment is going to be a segment that connects the midpoints of two sides of a triangle. So if you think about here, D and E are midpoints of each of those sides. And we know that because see these marks here? I know that the distance from A to D is the same as the distance from D to C. I know that the distance from C to E is the same as the distance from E to B. So that segment DE is our mid-segment. And we're going to find out some cool characteristics of it, one of which is that it is going to be parallel to, and we're going to call this the third side. The first two sides are the sides that are involved in the creation of that mid-segment, and it's going to be parallel to that third side. All right, next up, we have a perpendicular bisector. A perpendicular segment, ray, or line, whatever we have that bisects this segment. So a perpendicular segment, ray, line, or plane to a segment at its midpoint. So it bisects, it cuts in half. So the distance from A to P is going to be the same as the distance from A to B. All right, when we talk about an angle bisector, a segment, ray, line, or plane that divides an angle into two equal parts. So when we put these bands on, we separate them a little bit just so you can see that we're talking about these two different angles. So if I have X degrees and X degrees, then I know that those degree measures are the same and that angle's space is bisected. A couple important things to talk about. When we measure a distance from a point to a line, we're always going to do it using a perpendicular line segment. So we learned from Pythagoras that this, and I want you to check out this diagram below here, this hypotenuse, this longer side of the triangle is going to be the longest side. So we want to make sure that when we're measuring from a point to a line that we're not going to involve any kind of angles and therefore increase that measurement. We want to make sure that we're measuring perpendicular from that dot to the line because it's going to be the shortest distance. So we always want to make sure that we are keeping in mind that that distance has to be the shortest distance possible using that perpendicular segment. All right, given those cool, oh, we also want to talk about the idea of equidistant. By definition, equa means it has the same. And we can say that two things are equidistant if the measure from one point or a line to another is the same. And keep in mind, that's always going to be measured with that perpendicular segment. All right, so our first cool thing that happens is that mid-segment that we create from the midpoints of two sides of a triangle. We already talked about how it's parallel to that third side, that mid-segment that's created from the midpoints. And I know that they're midpoints because of these markings on my triangle. So not only is it parallel, but it's also going to be half the distance. So the distance from D to E is going to equal to the half of the distance of A to B. We could also say that twice DE is equal to AB. And we can say that this distance here is going to be that there. The segment containing the midpoints of the two sides of a triangle is the midsegment. It's parallel to the third side, and it's half as long. So I know you're curious. You're like, wait, I totally want to prove that. So how can I prove this theorem? Well, wait no longer. Ta-da! We can start putting our triangles on a coordinate plane. we can start looking at coordinates, xy ordered pairs, for our vertices, and we can start using our formulas for distance and slope and midpoint to help us out with those conversations. So let's talk about a coordinate proof. So if we're given E is over here at negative 3, 4, D is here at 5, 4, C is down here at negative 3, negative 2, and FG is a mid-segment. And we can kind of already see that because if this distance here is 1, 2, 4, 5, 6, here's F's ordered pair. And if G is 1, 2, 3, 4, 5, 6, 7, 8, halfway between my x coordinates. All right, so here's our proof. We've been given these coordinates. We'll go ahead and talk about the coordinates for F. Over negative 3, which is the same as E and G, but then its y coordinate is going to be up 1, which is going to be half of the distance between 4 and negative 2. And we can talk about those calculations that we can get from those midpoints by using our midpoint formula. So it's x1 plus x2, my average of my x coordinates, and then of course the average of my y coordinates. So when I'm talking about the midpoint from E to C, my calculations are going to be negative 3 plus negative 3 divided by 2. That's the average of my x coordinates. The average of my y coordinates are 4 plus negative 2 divided by 2. Therefore, that xy ordered pair is negative 6 divided by 2 is, of course, negative 3. And then where did I drop my negative? Plus negative 2 divided by 2. That's positive 2 divided by 2 is 1. Holy cow. There we go. Negative 3, 1 is going to be my coordinates for F. All right, let's do the coordinates for G. Looking across on my graph, the average of my x's is going to be negative 5 plus 3 divided by 2. That puts G at 1. And of course, my y coordinate is going to be 4. So what's new is I can talk about my justification for that is the midpoint formula. How did I get those values? I put it through this midpoint formula to find those coordinates of F and G. All right, so now we're going to move on and talk a little bit about slope. So slope, when we talk about that formula, my slope is equal to y2 minus y1 over x2 minus x1. So when I want to find the slope of segment FG, it's going to be these coordinates that I use. So we'll come down here, and I gave you some room for some calculations. So my slope of segment FG is going to be equal to the difference between my y's compared to the difference of my x's. So I wind up with positive 3 over positive 4. And I can verify that. Do I rise 1, 2, 3 and run 1, 2, 3, 4? Yep. That sounds about right. So my slope of FG is going to be 3/4. All right, let's talk about my slope of CD. So my slope of CD, if I go and get those coordinates from up here, my slope is going to be my y2 minus y1 over x2 minus x1. So that's going to give me -6 over -8, which of course simplifies to +3/4. And I can double check that also on my grid. Rise 1, 2, 3, 4, 5, 6. Run 1, 2, 3, 4, 5, 6, 7, 8. So if you notice, I have the slope of 3/4, and I can put into my proof the slope of 3/4, and my justification is that I used this slope formula and I did these calculations. All right, now let's talk about the distance from F to G. My distance formula is, my distance is equal to the square root of the average of my x coordinates squared plus the average of my y, the difference of my y coordinates. So x2 minus x1, y2 minus y1. What's nice is if I've already done slope, I already have those values right here. So for the distance from F to G, that's going to be equal to the square root of the difference between my x coordinates, which was 4 squared, plus the difference between my y coordinates, which was 3 squared. So the distance from F to G is going to be equal to the square root of 16 plus 9, the square root of 25, which is equal to 5. Now let's come on over and do the distance from C to D. So if I want to know the distance from C to D, I say that's equal to the square root of my difference between my x coordinates squared and the difference between my y coordinates squared. So to go back up to this work I did here, the difference between my x coordinates was -8. The difference between my y coordinates was 6. So the distance from C to D is going to be equal to the square root of 64 plus 36. So the distance of C to D is the square root of 100, which of course is equal to 10. So I can fill 10 in for my distance from C to D, and my justification is the distance formula. That distance formula justifies what I'm doing. Here's my statement. Therefore, FG is a midsegment. FG is parallel to CD. And FG equals 1/2 of CD. So that's what I was asked to prove up here. And I could say, therefore it is, and I can do that by, check out what we have up front here. My mid-segment theorem is going to justify the fact that it's parallel to the third side and half as long. And it contains the midpoints. Therefore, by the mid-segment theorem, I know that FG is a midsegment. All right, taking a look down here, what congruent triangles can you find in the diagram? Hey, this is kind of fun because U is the midpoint because it divides QR in half. U's midsegment is here. It's parallel and half the distance. S is a midpoint because it divides QP into half into two congruent segments. S is midsegment is right here at UT. And guess what? It's the same length as 1/2 of those segments. Can you guess what I'm doing next? T is the midpoint of RP, dividing this segment into two congruent pieces. US is the mid segment that is parallel to RP and half as long. Do you see in this diagram 1, 2, 3, 4 congruent triangles? And they're all justified by side, side, side congruence. Check it out. Everyone has a side that's 1, 2, and 3 hash marks long. All right, next step. We're going to talk about the perpendicular bisector theorem. Hey, your perpendicular bisector, we've already made these by construction. So you should kind of have an idea of how we go about doing this. Don't we create a segment? And then don't we find a point above and we find a point below the line that we can then connect for our perpendicular bisector. And we find that this will bisect the segment in half at a perpendicular angle. Well, here's something really cool. If a point is anywhere on this perpendicular bisector, it is going to be equidistant from the endpoints of the segment. So any point on this perpendicular bisector is going to be the same distance from A to B. That's why when you drew your perpendicular bisector as a construction, it didn't matter how long you made it or how big or wide open your compass was. Any point that's on this perpendicular bisector is going to be the same distance to those endpoints. How cool is that? If CP is the perpendicular bisector of AB, then I know the distance from A to P is equal to the distance from B to P. Hey, guess what else I know? I know that the distance from A to C is going to be the same as the distance from B to C. I could name a point down here and say that the distance from this point to those two places is going to be the same too. All right, our converse of the perpendicular bisector theorem says the same thing, but in reverse. If you have a point that's equidistant from those endpoints of the segment, then it's on the perpendicular bisector. So if the distance from A to P is the same as B to P, then guess what? That segment is on the perpendicular bisector. Same as if the distance from A to D is the same as D to B. D is on that perpendicular bisector. In the same vein, we can talk about angle bisectors. If a point is on the angle bisector, it's going to be equidistant to the sides of the angle. Now, this is where it becomes super important that we measure that distance with that perpendicular line segment. We need to make sure that we're understanding that when we measure this distance, we're doing it with that perpendicular segment. If a point is on the bisector of the angle, then it's equidistant from the two sides of the angle. And guess what? I can measure that at any point, whether it's where the mouth of the angle is open real wide or close in tight. If it's sitting on the angle bisector, it's equidistant. All right, the converse is true also. If a point is in the interior of an angle and it's equidistant from the sides, then that segment that it's sitting on is an angle bisector, and we'll cut that angle's measure in half. Okay? In this diagram, BE is the perpendicular bisector of AC. So I know that this is congruent to this, and that's a perpendicular relationship, so a right angle. What segment lengths are equal? What information would you need to conclude that BE is also an angle bisector? I'll let you stew on that for a little bit. In the diagram, D is on the bisector of angle ABC. Even though we can't see it, we know that a bisector exists here and D is sitting on it. What is the distance from D to C? And then be able to explain your answer. All right, so I'm going to leave you to go ahead and think about these two questions and practice your segment lengths on the back. Come with questions and we'll talk more tomorrow. Bye.